So it says if an integer is not divisible by 3, then the square of this integer, let's say this integer, let's call it n. If an integer n is not divisible by 3, then n squared must be equal to 3k plus 1 for some integer k. Okay, so here we know that we know what? We know n is not divisible by 3. So the square of this one, naturally, it is not divisible by 3. But if a number is not divisible by 3, it doesn't mean that, so this is the square. It doesn't mean that it looks like 3 times something plus 1. It could be 3 times something plus 2, right? Because there are two different kinds of integer that is not divisible by 3. One is like 4 or 7 or 10. So these are multiples of 3 plus 1. But then you have another kind, like what? Like 8 or 11 or 14. So these kind of integers, they are the multiple of 3 plus 2, right? So there are two different types. But here it says that no matter what n is, as long as n is not an integer divisible by 3, then the square must be of this type, 3k plus 1 type. So why? Or how? Okay. So this is a perfect example for proof by cases, because there are not many different cases. Okay, so what are the cases here? So it is of this form P implies Q, right? So it is of the form P implies Q. P is an integer not divisible by 3. So if an integer is not divisible by 3, can we make it into smaller cases to consider? Not divisible by 3, it could be a multiple of 3 plus 1 or a multiple of 3 plus 2. Am I correct? So we can divide this into case 1. So case 1 is n is something like 3 times m plus 1. So this is case 1. And then we can have a case 2 here. Case 2 is n is of the form 3 times m plus 2. Now as long as in these two cases we can show that the resultant n squared will be of 3k plus 1 type, then we are done. Because we are showing that both cases lead to the same conclusion. So it means that all cases, any cases, will lead to the same conclusion. Is that okay? This is what we want to do. So case 1 is 3m plus 1. So n squared is equal to 3m plus 1 square. Is that okay? And then if you expand it, this will be equal to 9m squared plus 6m plus 1. Is that okay? Is that okay? And then you can see that this 9m squared, it is a multiple of 3. This 6m is also a multiple of 3. So altogether, this is a multiple of 3. This is 3 times bracket of 3m squared plus 2m, okay? And then plus 1. So in this case, it is okay. So this is okay. How about case 2? Case 2 is n squared is equal to 3m plus 2 square. Is that okay? So this is equal to, if you expand it, this will be equal to 9m squared plus 12m plus 4. Is that okay? Plus 4. So you take out 3 outside, so you will actually have 3 times 3m squared plus 4m plus 1 and then plus 1. Is that okay? And then done. Okay? Is that okay? Good. Good. Done. Okay, done. Okay, now how about the Black Friday problem? Okay, so let's do this. So a year could be a normal year or could be a leap year. So there are two cases, different kinds of years. So normal year or there is a leap year. So leap year has one more day, 366 days. And then normal year, there are 365 days. So let's do normal year first, and then we will leave this for you as an exercise at home. If you can prove that every normal year there will always be a Black Friday, and every leap year there is a Black Friday, then you prove that every kind of year there will be a Black Friday. Is that okay? Now, how can we simplify the proof? So let's do this. Okay, so let's do this. So let's forget about whether we are looking at a specific year. Let's look at which day is each of these 13th of the month around the year. So for instance, in January the 13th is going to be the 13th day out of these 365 days, right? So the first January the 13th, so this is the January the 13th, is going to be at day 13. Is that okay? Is that okay? Good. How about, so let's say this should be the date, and then this should be the day, okay? How about the February the 13th? February the 13th is going to be 31 days after this January the 13th. Am I correct? You add 31, so it is going to be 44, right? Is that okay? And then March the 13th is going to be 28 days after this day. Is that okay? So this will going to be 72. Is that okay? Now April the 13th will be going to be 31 days after this day. So it will be what? 103. Is that okay? So this is April. Yeah, don't be lazy. Let me write down. So April the 13th. How about the May? So if it is May 13, then it will be adding 30 to this. This will be 133. And then June 13, this will be adding 31 to this one. It's 164. So far, if you understand what I'm doing, could you please raise your hand? Okay, excellent. Okay, and then what? And then what? And then July. So it is 194. August 13, it will be, you add 31 to this, it's going to be 225. And then September 13, it is going to be adding 31 to this one, so it is going to be 256, right? And then October 13, it is going to be adding 30 to this, is 286. November 13, you add 31 to this, so it is going to be 317. Is that okay? And then finally, this is December. December 13, you add 30 to this, 347. Okay, now to make, because we are focusing on which day of a week we are looking at, so we are actually interested in something that is, you divide it by 7 and take the remainder after dividing by 7. So let me change each one of them to something like the day modulo 7. You have studied this one already in your computer programming, right? This is to divide 7 and then take the remainder, okay? So 13, you take the modulo 7, it is equal to 6. Is it okay? And then 44, you take this one modulo 7, is equal to 2. Is that okay? And then 72, 2, 103. 103 is equal to 5. Is it? 5. Looks like 5. This one, 133. 133, 0. 133 is a multiple of 7. It's a 0. Is it okay? It's a 0. Okay. 164, 3. 194. 194 is what? 194 is what? 195? Is it 5? Yes, 5. Okay. 225? 225, 15. 1. Okay, very good. 256. 256. 4. Okay, good. This one I know, 6. This one 2. No, is it 2? 2. Okay, good. 2. And then this one is minus 3, so it is 4. Is it? Okay. Is that okay? Now, what do we know? What do we know? So we prove it by cases. Okay. So the cases is like this one. If this one is a, let's look at this. If this one is a Saturday, what does it mean? If this one is a Saturday, then this one is a Tuesday. This one is a Tuesday, this one is a Friday. Is that okay? So if this one is a Saturday, then we have a Black Friday here. Okay? Now, if this one is a Sunday, then what does it mean? Then this one is a Wednesday, this one is a Wednesday. This one is a Saturday. But then this one will be a Friday. Is that okay? If this one is a Monday, then you are actually adding 2. Then you will have this one will be a Friday. Is that okay? So if you look at it, you have actually 0, 1, 2, 3, 4, 5, 6, all of them. All of the remainder of 7 appears. So what does it mean? It means that no matter how we change this one, then you still have, you change this one, it means that you are adding some number here. You add x to it. And when everyone adds the same x, you will still have all the 0 to 6, 0, 1, 2, 3, 4, 5, 6. So it means that no matter which day this day it is, so there are 7 cases, you must have a Black Friday somewhere. Is that okay? So that means that in a normal year, you must always have a Black Friday. And of course, okay, so we can actually do the leap year. So what is meant by leap year? Leap year means that on February, you have 29 days. Okay, so in that case, this one is no longer 2. This one will be leap year. This one will be 3. Is that okay? Actually, everyone after this day, you add 1. So this is a 6. This is a 1. And this is a 4. This is a 6. This is a 2. This is a 5. This is a 0. This is a 3. And this is a 5. Let's check. So here you have 0 here. You have 1 here. You have 2. You have 3. You have 4. You have 5. And then you have 6. Is that okay? So in that case, you have 0, 1, 2, 3, 4, 5, 6. And then there is always a Black Friday. Okay? And if you wish, I guess you may, let me check. So 1, 2, 0, 1, 2, 3, 4, 5, 6. Actually, no matter which case, you will find 0, 1, 2, 3, 4, 5, 6 only in these 8 months. So you can actually make your argument stronger. So every year, there must be a Black Friday from May to December. Okay, you can make it a little bit stronger. So you don't need the first 4 months. So the last 8 months, you must contain a Black Friday. Because in these last 8 months, no matter you are talking about normal year or leap year, you will have a 0, 1, 2, 3, 4, 5, 6. Yeah, here you have 0, 1, 2, 3, 4, 5, 6 in a leap year. And then in normal year, there is a 0, 1, 2, 3, 4, 5, 6. Okay. Okay, so the last 8 months, there will be a Black Friday. Okay, that's it. So here, this is something that is powerful. Okay, if you find something that is difficult to prove, chop it into cases and handle each case one by one. Okay, you can use further properties of each case to help you to prove something. Okay? Okay, so here we are going to prove equivalence. So we are proving equivalence. So for instance, if I want to show something P is equivalent to Q, some statement P is equivalent to Q, there is one method that we can show, okay? It is to show that P implies Q, and at the same time, Q implies P. Is that okay? So for instance, we have shown this. So for instance, this is something that we have actually shown before. Let n be an integer. Then we are showing that n is odd. Let's say this is what we want to show. N is odd if and only if n square is odd. Okay? This is what we have not shown exactly this argument before. We have not shown if and only if before. But let's say this is P, this is Q. So P implies Q. Is it easy to show? So P is n is odd. Q is n squared is odd. So is it easy to show? If n is odd, then n squared is odd. It is easy because we can use direct proof to show it. For this one, we just assume that n is equal to 2k plus 1 and check what is happening about 2k plus 1, this one all square. We find that this is also odd, so we can show P implies Q. Is that okay? Okay, how about Q implies P? Q implies P. Q implies P. If we know that n is an integer and also n squared is odd, how can we show that n is also odd? We have done this before. We can prove this by indirect proof. Prove this by contradiction or by contraposition. So we have an indirect proof for this one. This one is equivalent to what? It is equivalent to not P implies not Q, right? Not P implies not Q. So we are actually showing, if we can show if not P then not Q, we can show Q implies P is also true. Now not P implies not Q means n is even implies n squared is even. So this is very easy. This again, you can use direct proof to prove this. Okay? Okay, so we have actually done this. This one we have shown this by direct proof. This one we have done this. Okay? So combining P implies Q and Q implies P, we have P if and only if Q. So these two statements are equivalent. Whenever I'm saying n is odd, I'm actually saying n squared is odd. Whenever I'm saying n squared is odd, it is the same as if I'm saying n is odd, because they are always having the same truth value. Okay? So this is the strategy. Usually, if you want to show this statement P and this statement Q, they are equivalent. Okay. Now sometimes there could be more than two statements involved. So perhaps we want to show that P and Q and R, these three statements are equivalent. So we want to show that P and Q are equivalent, and Q and R are equivalent, and P and R are equivalent. You want to show this. Okay. Now to show this, of course, we can do this one by one. But there is something that is a little bit cleverer. We can do something like this. Very interesting. We can do something like we just show P implies Q, and we show Q implies R, and we show R implies P, and then it is the same as if we are showing P implies P and Q and R. These three statements are equivalent. Now the reason, okay, the reason is simple. Okay. So why does it work? If you look at these two, if I can show Q implies R and then R implies P, what do I have? I have Q implies R, I have R implies P. What do I have? Q implies P. Is that okay? So if I can show this one and together with this one, then I'm actually showing P implies Q at the same time Q implies P. Okay, so I will have this part. So this part is okay. Is that okay? Now similarly, if I have this part, take this part here. If I have P implies Q and R implies P, what do I have? The first one and the last one, what do I have? P implies Q and then R implies P, what do I have? I will have R implies Q, am I correct? Is that okay? So I have Q implies R. These two gives me R implies Q. So I will have Q if and only if R. Is that okay? So I can also have this one. And finally, if I have this one, this is R implies P, right? But I have P implies Q, Q implies R. So I will have P implies R. P implies R there, R implies P there. Then I will have this one. So if the right-hand side are all true, then the left-hand side must be true. Is that okay? On the other hand, if the left-hand side is true, then this one is true, this one is true, this one is true, right? If this one is true, then this one is true. If this one is true, then this one is true. If this one is true, this one is true. So we will have everything true. Okay? Yeah, this one is true means that, why? I have this one. This one means that P implies Q is true, and then Q implies R is true. So this one automatically implies this one is true. Is that okay? Okay? So in that case, what does it say? The left-hand side is true, then the right-hand side is true. The right-hand side is true, the left-hand side is true. So left-hand side and right-hand side, these two are the same, equivalent. Okay, so let's take a, so this is just another way of interpreting, of understanding the left-hand side. But this will mean that we are just showing 1, 2, 3. 3 things correct instead of showing 1, 2, 3, 4, 5, 6. So this saves half of our work. Okay, so let's take a look at an example. So suppose that P is this argument, N is even. Okay? And then Q is this one, N minus 1 is odd. And then R is this statement, N squared is even. We want to show that these three statements, these three propositions, they are all equivalent. So how do we show? So we show, using our strategy, we just need to show P implies Q, Q implies R, and then R implies P. If we can somehow show this, this is done. Is that okay? So N is even implies N minus 1 is odd. So this is quite trivial, right? Right? Yeah, take N to be 2K. This one is 2K minus 1. So 2K minus 1 is equal to 2 times K minus 1, this number plus 1. So this is an odd number. Okay? Now, if I know that N minus 1 is odd, then how can I show that N squared is even? So N minus 1 is odd. So N minus 1 is equal to 2K plus 1 for some number. So N is equal to 2K plus 2 for some number, K. And then N squared, you do this by direct proof. Understand my point? Okay? So here, if I have this one, so N is equal to, N minus 1 is equal to 2K plus 1 for some integer K. So N is equal to 2K plus 2. Is that okay? So in that case, N squared is equal to blah, 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 blah. And then it is equal to 2 times some number M. So N squared will be even. Is that okay? Now finally, N squared is even. How do we show that N squared is even implies N is even? We prove it by indirect proof. Okay? So we assume that, yeah, N squared is even implies N is even. It is the same as if N is odd implies N squared is odd, and it is easy. Okay? So somehow, we prove this one, this one, this one, these three things separately, and then we can show that P, Q, R, these are all equivalent. So whenever someone says N is even, you know that you can replace the same sentence as N squared is even. Or whenever someone says N squared is even, you can replace this sentence as N minus 1 is odd, because they are all equivalent. So you say this one, it is the same as if you are saying this one. Okay? Good. Let's take a break. Okay, let's take a 10-minute break, and then we can come back with some more examples.